Hi, I'm CJ and I'm a mechanical engineering student.
Hi, I'm AJ and I'm a mechanical engineering student.
Hi, I'm Noah and I'm an optical engineering student.
Hi, I'm Colton Stoltz and I'm an electrical and computer engineering student.
And I'm Zach Rovig, an optical engineering student and team lead for team 19037. So our project was to develop a light guide plate for our sponsors, Honeywell Aerospace. A light guide plate is used in every LCD screen today as a part of the backlight unit. The light guide plate utilizes the phenomena of total internal reflection and a pattern of scattering features to provide a uniform illumination profile to the LCD panel. This is to ensure that there are no bright or dark spots on the viewing screen. To accomplish this, our sponsor gave us 3 requirements. 1, the LGP shall provide a 90% uniform irradiance profile. 2, the LGP shall provide an optical efficiency of 80%, and 3, the LGPs shall have an aspect ratio of 4:3 and 16:9 with diagonal lengths of 3 inches and 20 inches and a thickness between 0.5 and 5 millimeters.
To accomplish the system requirements, the team split the project into 3 main goals. First, to design an optical pattern for the LGPs with size, optical efficiency, and optical uniformity requirements. Secondly, to determine and execute a method to etch the optical patterns onto acrylic sheets. And third, to design and manufacture a test fixture to illuminate all sizes and orientations of the LGP. By categorizing the project into 3 main goals, we were able to best utilize the skills of each team member. As the majority of the project stemmed from the hardware that would be etching the patterns onto the acrylic sheets, the team first focused on finding the laser that best suited our needs. This proved to be extremely challenging, as the team was confined by a tight budget, a high resolution requirement, and the need for sophisticated software and a large working area. Ultimately, the team decided to go with the DIY Fabule CO2 laser. And although this laser met many of our requirements, we knew that significant modifications would need to be made. Once the team decided to purchase the Fabule CO2 laser, we could then break off into our respective disciplines and focus on the remaining tasks. The mechanical engineering students, CJ and I, could focus on assembling the laser and designing and building the test fixture, while the optical engineering students, Noah and Zach, could focus on aligning the mirrors of the laser and designing the optical patterns. And Colton, the electrical and computer engineering student, could focus on making the hardware and software modifications to the laser.
The hardware that came with the laser was actually precise enough to meet our requirements. The trouble that we were having was with the software that came with the laser. Whenever we loaded an image with the software, it would lead to image distortion, and that would directly transfer to anything we etched with the laser. So with that issue, we went ahead and decided to install a new controller. This new controller, which is called the Smoothie Board, it uses G-code to control the motors and the laser of our laser etcher. To produce these G-code files quickly and efficiently, we developed a GUI-based program called PatGen. PatGen was written by us and it uses the Python programming language. So our program PatGen, it will take in user parameters such as the aspect ratio of the screen, the diagonal measurement, and then the desired pattern that the user wants, and it will go ahead and convert those parameters directly into G-code. Another nice thing that the program does is it will convert any optical simulations that the team has done and convert that directly into G-code. Once PatGen finalizes the G-code file, it is then placed on the microSD card that is on the controller. Then the user can select which G-code file they want to play using either the attached LCD screen that came with the controller, or it can actually select which program it wants to play using a computer that's connected to the same network as the controller board. And once the G-code file is playing through the laser etcher, the user then can sit back and watch over the machine until it finishes.
To achieve our system requirements of a 90% uniform irradiance and 80% optical efficiency, we determined that Light Tools was our best optical software to do so. Light Tools enables us to change the size and dimension of our light guide plate, the number of rays, the density of dots, and other parameters for our optical illumination system. So additionally, we are able to use Light Tools so that we can have more control over what kind of patterns we are using and what kind of uniform output we are looking for to optimize our light guide patterns. We can do this to confirm our optical efficiency requirement by looking at the luminance plot given to us by our Light Tools software. Illuminance shows how much light per unit area on the detector that we get as we trace the rays through the simulation. However, this does not cover our uniformity requirement because it does not consider the angle by which we are looking at for our detector. However, we will be able to use the luminance plot in our Light Tools software to look at the different kind of solid angle and how much light we have per cone of solid angle. Thus, we can use our optical design software to confirm our requirements.
In order to test the light guide plates, the team had to make a test fixture that could hold 2 LED strips at 2 edges of the light guide plate. As mentioned before, the light guide plate had to have a diagonal length of either 3 or 20 inches. This proved to be the main challenge for the test fixture as it had to accommodate many different aspect ratios and diagonal lengths. To account for this, the team designed a test fixture in SOLIDWORKS made from a single sheet of 5052 aluminum. The sheet was designed to be cut, bent, and welded to form the basic shape of the test fixture. Along with this, a vice screw was added to help account for the different aspect ratios and diagonal lengths.
With the new controller installed, it allowed us to control the machine in far finer detail. With this higher level of control, it required quite a bit of fine-tuning and troubleshooting though. Configuration settings needed to be updated. Some of these settings included the duration of the laser etch, the steps per millimeter of each motor, the current going to each motor, and the speed of each motor.
Fortunately, we were able to continue our optical simulation using Light Tools at home. We were able to accurately simulate both our optical efficiency and our uniformity requirements using Light Tools for both our 4:3 and our 16:9 aspect ratios in our requirements. To find the optimal laser settings, our team was going to use our laser etcher and do various different experiments to determine what the best laser setting was, and then analyze the results under a microscope. Fortunately, we were able to do a bunch of different experiments to determine what the best depth was and the best laser power to use for our light guide plates. However, we were not able to take them into the lab and look at them under a microscope to determine the ideal roughness for our light guide plates.
Before spring break, the main frame of the test fixture was cut and bent to shape. Due to the COVID-19 situation and most machine shops being inaccessible by the team, we were unable to weld the LED support frame to the test fixture as originally intended. To account for the lack of welding materials, I was able to attach the LED support frame using spare nuts, bolts, and angle brackets I had around my house. This didn't negatively affect the structural integrity of the test fixture, and it fully allowed us to finish the structure of the design.
Like the rest of the world, our team has been forced to adapt and to overcome the new challenges we have faced. Unfortunately, without the tools required, our team was unable to test the efficiency and uniformity of the light guide plates. However, we were able to complete the laser etcher assembly and modifications, the final optical pattern designs, and the test fixtures. Even with limited resources, our team was able to collaborate safely and efficiently, and we consider the end result to be a success.